Okay, now that Hap is here, we can start. Well, thank you all for coming. This today we will continue with a sequence of lectures that are dedicated to the inner workings of the plant. And the goal of my lecture is to try to bridge some of the ideas that have been presented by Wilfried Conrad and Nadine, and as well as Kari Jensen, a little bit down the road. So perhaps you could view this lecture as more of a stitching lecture between the various phenomena that have been presented in the other two lectures. Okay, so to start with, I'd like to thank my collaborators from Duke University, Jean-Christophe Domecq, Ram Oren, and Sari Palmroth, from ETH Zurich, Gabriele Manoli, who was a previous postdoc at Duke, from Nagoya University, Taro Nakai and Tomo Kumagai, although Tomo just moved to Tokyo University. From University of Helsinki, Samori Loinanyan, who is now at Luke. From University of New Mexico, Shengwei Huan, who just finished his PhD with me and has started his postdoc there. From Padova, Valeria Volpe, who visited Duke University for about a year in 2011, and Marco Marani, who's a colleague of mine who has a joint appointment between the two institutes. Tanos Paschalis, who was a former postdoc of mine, and now he's at the Imperial College in London, has also done some work that I'm presenting. Stefano Manzoni, who was a student postdoc at Duke University, now at University of Stockholm. Wilfried Conrad, Danielle Way, who is now at University of Western Ontario, and she used to be a postdoc at Duke University. And Julia Vico, who is now at the Swedish University of Agricultural Sciences, and she used to be a postdoc with me and Amilcare Porporato. Okay, so to start this discussion, it's hard to come up with a good starting point for biosphere-atmosphere exchange. The study of evaporation probably dates back thousands of years, and it is almost impossible to do justice and cover all the literature that is relevant to at least that topic on its own, just evaporation. But perhaps a major turning point has occurred when the kinetic theory of gases was proposed. And what we will do is try to start the discussion here from this point onwards, realizing that by no means this is doing justice to the whole literature that has been developed up to the point of the kinetic theory. The reason this point is chosen is that it's a point that is basically associated with the phase transition, and it's the first time we started viewing the phenomena of biosphere-atmosphere exchange, perhaps from a microscopic view. So again, a brief summary of accomplishments that have occurred. In 1738, Daniel Bernoulli published his book Hydrodynamica, and the basis for the kinetic theory of gases was actually proposed in chapter 7. And I should say that the current textbooks that you see today are still teaching this topic exactly like Daniel Bernoulli did in 1738. Okay. In 1801, Dalton, actually building on some of the ideas in Daniel Bernoulli, proposed the law of partial pressures. Also, the first evaporation equation was proposed by Dalton then. In 1857, Clausius took the work of Daniel Bernoulli one step further. He noted that particle motion actually has both translational, rotational, and vibrational components. So that allowed actually the kinetic theory of gases to be extended to basically all matter. Yeah, including liquids and solids. And in this paper, in 1857, Clausius actually was the first to introduce the concept of mean free path. Maxwell derived the statistical distribution of the kinetic energies themselves, and it was Boltzmann who put all the pieces together, where the connection between entropy and probability was first stated. And in it, we finally had a unified picture of the classical laws of thermodynamics and statistical mechanics. So when you discuss evaporation to colleagues in physics, they say, what's new? Okay, we almost know everything. Okay, and at some point, if you have a closed system, we're subject to a constant temperature. So this is an equilibrium system that has liquid and gas drawn over there, or I should use this one, drawn here. We know that the kinetic energy distribution of these molecules follows the Maxwell-Boltzmann distribution. And so, there is always a finite probability that one of those molecules is going to jump out. And if you increase the temperature, you basically increase the kinetic energy of those molecules, so more of them can jump out. And at some point, you're going to reach a phase where the number of molecules that are jumping out is going to be balanced by the number of molecules that are going to simply recollide back with the water surface. And hence, you reach a phase where at a given temperature, the net evaporation rate is zero. And in fact, it is the saturation vapor pressure of these molecules that follows the Clausius-Clapeyron equation. That's why it's dependent on temperature. Okay, so in a closed system, we seem to understand what's happening, but that's not what occurs in nature. Why is that? Well, two things. First, the system that we're dealing with is actually open to mass and open to energy exchanges. Okay, so let's start with the opening of this box to flow. The idea then is that these molecules are no longer just jumping based on mean free paths, but now there are coherent eddies that are moving them. Is by no means a new concept. Boussinesq in 1877 attempted to study the assemblage of swirling eddies, as they call them, swirling and agitated flow in liquids. Now we call them eddies, and it was a major hallmark in the study of turbulent flows, even though the word turbulence was not yet invented. It was not even invented at the time of Reynolds. In fact, it was proposed after Reynolds' experiment. So we didn't have even a word for turbulence. But in this paper of Boussinesq, he proposed the concept of eddy diffusivity or eddy viscosity. And that actually happened way before Reynolds' famous experiments, because in fact, Boussinesq's paper proposed a local averaging concept. And he also proposed the concept of mixing length to resemble basically Clausius mean free path length. And that idea actually inspired later von Karman and Prandtl to propose their log law. And in fact, if you look at Boussinesq's paper, what is interesting about it is that he attempted to formulate it in tensor notation. So in other words, it was the first attempt to actually look at these equations using tensor point of view. And he showed that the Reynolds stress, what we call now Reynolds stress, and the mean strain rate tensors are actually aligned, and that was the first results. And in fact, if one reads Boussinesq's paper, there are plenty of mistakes and left and right assumptions that are contradictory, but these ideas have been certainly put forth in a major way, and they were maybe, if you like, cleaned up a little bit by Osborne Reynolds years later. Okay, so now we have a basic idea that allows us to think of movement in this box when it is opened up, rather than having a mean free path that is based on molecular kinetics. They are now based on turbulent transport processes. Now the box has to be opened up also for energy exchanges, and perhaps the work of Ira Bowen in 1926 is not the first, but certainly the most influential. The concept of what we call now Bowen ratio has been around for a long time, but Bowen was the one who pushed it on force with a study on lake evaporation. And in fact, just to bring up the issue in terms of graduate students here, you see, Ira Bowen was not even interested in this project. He was told by his advisor, Robert Millikan at Caltech, that he needed to help a student finish his PhD. And so the student was working on evaporation from lakes. And so basically, Ira Bowen had to drag the student and figure out how to estimate evaporation from lake. But Robert Millikan was quite astute about energy and ions and so forth, and so Bowen had that foresight, and of course he immediately approached the problem from the perspective of an energy balance, and he basically wrote the net radiation minus the soil heat flux, or actually at the time water flux, the heat flux that enters the water surface must be balanced by the sensible heat flux and the latent heat flux. And then he used ideas similar to Boussinesq, where he introduced the eddy diffusivity. So he assumed that the sensible heat flux somehow scales with the temperature gradient multiplied by an eddy diffusivity for heat. Likewise, for the latent heat flux, scales with the water vapor concentration gradient multiplied by the eddy diffusivity for water vapor. And he immediately realized that if he divides the two, he gets the Bowen ratio as a function of the change of water vapor concentration with the change in temperature. And he was able then to reason incorrectly, in fact, because he made the argument that if the eddy diffusivity of heat and water vapor resembles those of molecular diffusion, so in fact he assumes that the ratios of eddy diffusivities of heat and water vapor is the same as the molecular diffusion coefficient of heat and water vapor. And he was lucky because they're not that far off in this case, but they could have been far off in other cases. so, so he made this analogy, canceled the ratio of the eddy diffusivities, and ended up with what we now call the Bowen ratio. And that allowed the estimation of the latent heat flux to be dependent on the measured available energy and the Bowen ratio that now can be inferred from atmospheric measurements. Okay, so that allowed the box to be open for energy. But then for operational purposes, in fact, Penman took it one step further. He looked at Bowen's analysis, basically replaced anything that has derivatives with differences, did a little bit of linearizations, and came up with what we now call the combination equations. And interesting enough, a few years later, the literature in the West translated the work of Monin and Nabokov that was probably written in the late 30s. And in it, they actually proposed, as John Finnegan mentioned yesterday, a revision to the eddy diffusivity to include now stability correction functions. So up to this point, we seem to have an analog to molecular motion, except that now the eddies are much bigger and the effect of thermal stratification could be taken into account. But up to this point, there is no plants in the picture or the story that we are weaving. Okay. The plants actually were introduced by Monteith in 1965, where he, in fact, revised Penman's equation to include the stomatal conductance on top of the aerodynamic conductance. But how do you go about specifying the stomatal conductance turned out to be a major, major hassle. Jarvis took this task upon himself to figure out how to do that. And as is the case in fields that are in their embryonic form, to borrow a word from Wilfrid, what you typically do is you have a maximum rate and a bunch of reduction functions, and you basically try to figure out what these reduction functions are from some maximum rate that you think you could estimate. And that turned out to be in the case of stomatal conductance to be dependent on photosynthetically active radiation or light, vapor pressure deficit, leaf pressure, atmospheric CO2, etc. And if you track actually a lot of the history of science, a lot of the assemblage of information typically is done like this. This equation, if you ever studied erosion, resembles the universal soil loss equation, if you ever heard of that. And in fact, the universal soil loss equation for erosion looks exactly like this. The erosion rate is normalized by some maximum theoretical value, and there are a bunch of reduction functions that depend on the intensity of rainfall, how loose the sediments are, etc. So you could see that the approach is typically to collect a lot of field data or a lot of data on this phenomena and organize it in a certain way, catalog it in a certain way. This is a very useful approach. And in fact, Jarvis did exactly that. Now, I should also mention the book by Wilfrid Broussard, Evaporation to the Atmosphere, because it was one of the first books on this topic that dealt with it exhaustively from the days pre-Greek up to the present. At the time, it was 1982. Okay, but then what happened is that by the early 60s and onwards, numerical experiments were being conducted on the climate. And in fact, the realizations from these climate models is that there is quite a bit of sensitivity of what's going to happen to the climate in terms of how surface evaporation and transpiration are specified. No surprise, because if you're interested in precipitation, the dynamics of the boundary layer are going to be important. And of course, those are going to be highly dependent on how you specify the evaporation rate and the sensible heat flux that drives the growth of the boundary layers. And in fact, this sensitivity to the land surface led to perhaps the first large-scale field experiment in our field, which is called the Haupex-Mobilly experiment in 1986, conveniently located in a nice place in France, southern France. But this was the experiment that was conducted on what was perceived to be at the time a GCM grid cell, 100 kilometer by 100 kilometers. So they actually took 100 kilometer by 100 kilometer and instrumented the living daylights out of it, including flux measuring stations, aircraft, sounding, remote sensing products that were pretty primitive at that time. But the era of large-scale field experiments started, basically, from this experiment onwards. One was in the US, and then there was a whole bunch in many other places. And in fact, this push to gather information on such large scales actually forced the remote sensing community to start developing products that can be interfaced with those sorts of experiments with the plan that it will feed into climate models. And In parallel for the water vapor, of course, the Hapex Mobili had no CO2. It was all transpiration and evaporation and so forth, because they were interested in boundary layer dynamics. Now, for the CO2, there was a parallel story that was developing. In fact, this parallel story perhaps might be traced back to Jan Baptist van Helmont, who coined the word gas in the 17th century and noted that the gas sylvestre, which is carbon dioxide, is given off by burning charcoal. He also, in fact, investigated water uptake by a willow tree, so in fact, he might have been thinking about this connection way back. And some people credit him for pioneering some of the earliest experiments on gas transfer. Now, so you could give the Belgians a thumbs up. This was major. But centuries later, in fact, Van Helmont's activities almost converged into a modern-day story. Atmospheric CO2 is largely rising because of fossil fuel combustion. And one of the leading mitigations that we have at our hand is the ability of plants to uptake CO2. So ironically, we are back to Van Helmont. Okay. But the important point here is that the role of stomata became more evident, and its control on the climate system became even more pressing as the carbon cycle is being coupled to the water cycle. So this coupling between the two alerted basically the climate community that carbon dioxide and water and the global carbon cycle and the global water cycle are so tightly coupled because of what the plants are doing. And you see very high profile papers, this is just a summary of a few of them. On the carbon cycle, it was recognized that reduced stomatal conductance because of elevated atmospheric CO2 would lead to saturation of uptake by plants, but of course you could still have because temperature goes up, respiration processes are going up, CO2 concentration goes up, so warming will have a positive feedback. So you increase temperature, you increase CO2 emission, temperature goes up. And that's because primarily the biosphere has saturated in its ability to uptake carbon dioxide. And that was kind of the idea behind a very influential paper by Peter Cox from the Hadley Center in 2000. The water cycle, there is a whole bunch of them as well. This is just picked, a few of them are picked here, that they deal with the continental scale runoff. And primarily the argument is that if plants open their stomata less, precipitation statistics are probably not changing, transpiration will go down, so continental scale runoff will go up. And there are many other papers that have popped up since then. I'm showing here a figure from a paper by actually led by the Dutch group, primarily by Susan Steele-Dunn, and they actually attempted to investigate the recycling ratio of water. And what you see here is how much of the water that you see in precipitation actually came locally from the land surface, and primarily more than half of the water that we have, or actually we use, is recycled water, except if you go, of course, to the edges where you have now water vapor coming from oceans. But the majority of the land surface actually sees precipitation as an outcome of recycled evaporation. Okay, so this is all fine and dandy, and we are beginning to understand better the role of stomates. But recently, in fact, we are now confronted with more pressing problems on top of that, which is now the effect of climate on plants. So we've been dealing primarily with the effect of plants on climate, but there is another side to this coin, which is the effect of climates on plants. And that tended to be accentuated primarily in the news after a sequence of droughts have hit many areas around the world. And the question of forest mortality and food security and so forth started popping up. And this is just a picture taken from the Food and Agricultural Organization review, where they were documenting the intensification of droughts in many long-term field experiments. And clearly, any attempts to study now the effect of climate on plants, not the other way around, would require a much deeper probing into how carbon and water moves into the plants. And that's what we're going to do now, as a complement or a supplement to Wilfried's talk and Nadine's talk. Okay, so this we have seen a little bit this aspects of these processes before. So what's happening inside the plants? Well, at the leaf scale, we know that when stomata opens to uptake CO2 and photosynthesize, water vapor is escaped. Now, this water vapor is basically supplied from the soil through the xylem all the way up to the leaf under tension, as we have seen yesterday. But ultimately what happens is that the products of photosynthesis are primarily carbohydrates and sugars, are then pushed back down to where they are needed, basically to cover the sinks, to grow biomass, etc. And in each one of those compartments, the leaf, the xylem, and the phloem, we have a set of governing equations that describe water movement or sugar movement or the coupling between water vapor and CO2. And these ideas are by no means new. So for example, in the case of the leaf, it has been recognized by Francis Darwin way back in 1898 that stomata actually controls transpiration rates. That was a major result, but it was known even before Francis Darwin that this was the case. And in fact, the amount of water vapor that can leave the stomates or the amount of CO2 molecules that can enter the stomate are primarily described by Adolf Hicks's approach, and this was known since 1855. In terms of water movement in the xylem, Wilfried mentioned yesterday cohesion tension theory. This was somewhat known here and there before, but it was formalized by the work of Dickson and Joly in 1894, to the horror, by the way, of Francis Darwin. He was entirely not convinced by this idea, and for good reasons at his time. He actually called cohesion tension theory as ropes of sand, basically, because the tensile strength of water was not known at the time. Okay? So the idea that water can withstand tension was completely off the wall. It was one of those miracles to him, you know. How could that be? So he was quite critical of the Irish duo, Dickson and Joly, but they persisted and continued on it. Now, in the case of phloem, we have a different mechanism. In fact, rather than water moving up the xylem under tension, in fact, now water is moving down with the carbohydrates or the sugars in the phloem under positive pressure. And that phenomena was recognized by Monk in 1930, and now it is called the Monk hypothesis, where basically you have osmoregulations. You build up sugar, water is pulled in, it gets pressurized, it pushes basically water down into the phloem. And so you have positive pressure down, negative pressure up, and the exchange processes are happening at the leaf. So clearly, if we want to now think of a general theory for water movement in plants, we have to almost couple these processes. And that is an important question. Are they really coupled, or are they really operating autonomously? And that's an interesting problem on its own. It's been recognized now in physics for some time that when you have networks on networks, you know, and that goes for power grids, that goes for many other types of networks. When you have networks on networks operating, in fact, the resilience diminishes. Because if something goes on with one network, all the other connected networks might actually collapse. However, it has been also recognized that natural networks that co-evolve appear to actually be much more robust. And Eugene Stanley, who did quite a bit of work in the past on diffusion limited aggregation, very famous in physics, is now almost picking this topic of networks on networks as a career and trying to open up this new field in physics of how do you deal with coupled networks together. So there is much more to this topic than just water moving in plants. Okay, so what we have now done is basically stated the basic mechanisms that are responsible for moving water in the xylem, in the phloem, and in the leaf. And in each one of those compartments, there are, of course, parameters that need to be inferred so that you could use these concepts operationally. And in the case of the leaf, you know, one of the concepts that was put forth by Ian Cowan and Troughton in a major paper in 1971, that stomata may have evolved so that it can maximize its carbon gain while preventing excessive loss of transpiration, means that now the leaf somehow is operating as an engineered system. It knows when to open the stomates and when to close them. And it wants to open the stomates in a way that maximizes the carbon gain. Now, of course, this is a macroscopic description. It's an outcome of many, many microscopic processes, but it looks like the plant has figured out a way to do that. In the case of the xylem, well, Wilfried mentioned a number of phenomena that are operating in terms of cavitation and safety, and same thing with Nadine stalk. And basically, the concept there is that plants have to deal, again, with another optimization problems. If they build very big vessels, they are more likely to cavitate. If they build very small vessels, they cannot transport water very effectively, but they are more robust to cavitation. So there goes another optimization problem. And in fact, in this case, the problem is framed more as a safety efficiency trade-off or runaway embolism versus hydraulic sufficiency. But it's another optimization problem, okay? that plants have to engineer a solution for it. And likewise, in the case of the phloem, as Jensen will discuss when he comes, but I will touch a little bit upon his topic, so we will make some contact with the phloem too, that the phloem vasculature is optimized for efficient sugar transport. And there again, there is another optimization problem. If you ram too much sugars because of photosynthesis, your viscosity actually will go up. Yeah, maple syrup. You now are dealing with maple syrup, very viscous, so it becomes much harder to push the water in the phloem. Okay, in fact, that's how you extract maple syrup. Okay, so that's the problem. So if you photosynthesize a lot, you produce a lot of sugars. That means that the viscosity goes up. But if you want to generate a large concentration gradient to push the water down in the phloem, you want that sugar concentration to be high. So again, you are faced with another optimization problem. So in each one of those compartments, what we're going to do next is discuss briefly these optimization problems, and we're going to end this lecture with a stitching mechanism between all these compartments. Hoping here, we're from the US, faith-based initiatives are becoming the norm in science. We're hoping that by stitching them together, we can add more constraints on the system. So in other words, if we treat each system in isolation, we have a large number of parameters. By actually coupling them all together, they will enforce certain constraints on each other, and that might make actually the problem more tractable. So did I set the background okay? Okay. As Wilfred would say, good. Let's start with the leaf. So what's the problem there? I mean, at a mathematical level, let's say, at a mathematical level, we do have a decent description of photosynthesis as a function of the internal CO2 concentration in the leaf. And that equation is often written as a biochemical demand. Photosynthesis is some saturation function of the internal CO2 concentration. And that the saturation function depends on two parameters, alpha 1 and alpha 2, and those actually are described by how photosynthesis is limited. It could be limited by enzymatic activity, or it could be limited by electron transport activity. But mathematically, alpha 1 and alpha 2 will vary in a very generic way with temperature and light, if you like, in more common terms. Okay, sounds good. That's helpful. So this is the demand by the plant. Where is the supply? The supply comes from the atmosphere. So you have CO2 molecules bombarding the leaf surface. If stomates open, some of them are going to enter the stomata. And how much will enter in terms of rate is going to be dictated by, well, some information about the porosity of this medium multiplied by the difference in concentration between atmospheric CO2 and internal CO2 concentration. So even if we know the environment around the plant, say temperature and light, so that we can estimate alpha 1 and alpha 2, and even if we know the atmospheric CO2 concentration around the plant, so that we can estimate atmospheric CO2, the problem is very much like what people in turbulence call the closure problem. Yeah, we have two equations and three unknowns. The unknowns are photosynthetic rate, internal CO2 concentration, and unfortunately stomatal conductance. So we need the closure model. Yeah, we need the closure model. And there is one approach to do that is you could say, hey, there is a wealth of empirical data that supports the argument that perhaps conductance, the stomatal conductance, must be proportional to photosynthesis. After all, stomates are opening to uptake CO2. And in a very famous paper by Ball and Berry, and later revised by Liuning, it was suggested that stomatal conductance must be proportional to atmospheric CO2, must be inversely proportional to the photosynthetic rate, inversely proportional to the atmospheric CO2 concentration, and somehow a measure of aridity, as Nadine Rohr mentioned yesterday, somehow a measure of aridity had to be taken into account. The original work of Ball-Berry, later popularized by Collatz, suggested relative humidity. Ray Liuning, realizing the weakness of the relative humidity as a metric of atmospheric aridity, suggested vapor pressure deficit, and his paper actually has a good following, so to speak. And both formulations have received quite a bit of support in the literature, especially the connection between stomatal conductance and photosynthesis normalized by atmospheric CO2. So this approximate linear relation between stomatal conductance, photosynthesis, and atmospheric CO2 is actually supported by a large wealth of leaf gas exchange measurements. And this version, in fact, of closure, if you like, when combined with the Fickian mass transport and the Farquhar photosynthesis model, was the basis of the first greening up of general circulation models in the mid-1990s, and it was described at length by a paper by Pierre Sellers. And in fact, Takahashi did a nice survey where he took all the Earth system models and the land surface models and tried to characterize how they are actually describing their stomatal conductance. And the ones that were in fact colored with purple are basically based on relative humidity, whereas the ones that are in somewhat green are based on the Lewning approximation. So you could see that the majority of these models are in use, they are quite popular, and so those closure assumptions are quite useful. Okay, so what's the problem? The problem is, can we do better? And part of the reason we would like to do better is that whether you describe this aridity index of the atmosphere based on vapor pressure deficit or relative humidity is a major factor. Why is that? Because it appears that climate models predict roughly a constant relative humidity, but they predict warming patterns. So if you are forcing the atmospheric aridity to be described by relative humidity, it means that the term in this equation is not changing much with climatic conditions. However, if relative humidity is constant and temperature goes up, vapor pressure deficit is going up exponentially. Yeah? And so in another case, it would suggest that the models that are based on vapor pressure deficit are in fact shutting down the stomata too much, maybe. Okay? So almost these two approaches might bind the end members of whether whether aridity of the atmosphere has a major impact on stomatal behavior or not. And that point was recognized way back by a number of collaborators of mine, including Tomo Kumagai from Nagoya University. Okay, now a different line of attack was taken on this problem, initiated by Ian Cowan, who John Finnegan just told me passed away recently, unfortunately. Ian actually came up with a very nice idea of formulating this problem, this disclosure idea, in a way that seems to be less ad hoc and perhaps is rooted maybe in a more general ecological hypothesis. He actually argued that plants must be somehow operating in a way to maximize their carbon gain while trying to minimize their water loss. Okay, and so there are many ways you could write this sort of optimization problem. But the idea is that as CO2 enters the plant, water vapor escapes through the same route. And if this is the case, if the stomata are somehow smart enough to maximize the carbon gain over a certain time period t, then there is an objective function for the opening and closure of the stomata. The objective function is to maximize the carbon gain, but of course there are some limitations on this objective function, and those come in the form of availability of water. Now, at that time, the availability of water was surrogated basically to transpiration rates, because there was no clear way of describing water availability in the soil in a clean way that then interfaces with a single equation for describing the fluxes of water in and out of the leaf, basically out of the leaf. So rather than force the objective function to be subjected to a soil moisture availability, what Ian Cowan did cleverly is he bypassed this problem and said, hey, what I really need to make sure is that the transpiration rate becomes finite. So that is basically suggesting that there must be enough water so that the transpiration rate is maintained finite. So that was basically the condition that he put. And you can always convert a constrained optimization problem into an unconstrained optimization problem using basically the approach of Hamilton and Lagrange. Okay, so that's a well-established trick. Constrained optimizations are no different than unconstrained optimizations if you introduce the Lagrange multiplier. And so basically one can write the Hamiltonian as photosynthesis that varies with the control parameter, which is stomatal conductance. Water vapor losses now can also be expressed as a function of this control parameter. Okay, and now we have basically an objective function that is strictly formulated with respect to the control parameter, in this case, stomatal conductance. So if we can maximize this Hamiltonian with respect to this control variable GS, then we are basically in business. And that might give us, in fact, a formulation for stomatal conductance with this goal in mind, okay? Maximization of this Hamiltonian, which is carbon gain subject to finite water losses. Clear? Okay. So let's recap. We have one equation for the biochemical demand. We have another equation for the atmospheric supply. When we balance biochemical demand with atmospheric supply, so that's already a major assumption, meaning that every single CO2 molecule that enters the leaf actually goes into, its fate is basically to be consumed by photosynthesis. We have two equations and three unknowns. If we add this optimality hypothesis of maximizing the Hamiltonian with respect to the control variable, then the problem can be mathematically closed. Okay? So that's an interesting result. But that makes the assumption that the Lagrange multiplier, which is essentially needed for this optimization problem, needs to be at least constant, or if it is going to vary. If it is going to vary, it has to vary on time scales much slower than the time scales at which stomatal conductance changes. Okay? So if stomata opens and closes, as Nadine has shown, you know, in time scales of minutes, then whatever boundary conditions that are going to influence this Lagrange multiplier, they have to change on time scales way longer than minutes. Okay? So this problem is mathematically closed. There are analytical solutions for it, and I'm not going to deal with them too much. But what I would like to do is give you a flavor of what these analytical solutions do. So to do that, we will look at a linearized biochemical demand function, just because the equations become cleaner and everything becomes evident. And in fact, if you like, the linearity of the biochemical demand function would be actually way appropriate if Rubisco limits photosynthesis. Okay. So now, if photosynthesis is linked to internal CO2 concentration, and the linearization happened here, basically, rather than have the denominator of this equation dependent on CI, we are replacing it by some sort of a long-term CI over CA quantity multiplied by CA. So that's how the linearization is done. Now, with this estimate of FC versus CI, we can get rid, in fact, of CI and combine the outcome with the Fickian diffusion model to write photosynthesis as a function of the control variable that we seek, which is the stomatal conductance. Okay, so now we have an expression for photosynthesis as a function of stomatal conductance. And there are a couple of features that we might point out, despite this horrible assumption that we made about the linearization. There are a couple of features that should be pointed out. First and foremost, this function has the right concavity. In other words, beyond Fe being 0, which is going to be precluded by our condition that transpiration has to be finite. Yeah. If you have a concave function like that, then you are going to intersect the transpiration rate. So your supply and demand will have an intersection point, which will be the optimal intersection point. So that is guaranteed basically by the curvature of this function. The second point, which is contradictory to perhaps what some politicians in the United States would argue, that if you keep increasing atmospheric CO2, the plants will be happy. No, there is apparently a finite limit that you could set on the biosphere, and that finite limit comes about also from this calculation that if CA goes to infinity, yeah, FC of GS does not monotonically increase with atmospheric CO2. Yeah, it actually levels off at alpha 1 over S, where alpha 1 could be the maximum Robisco, VC max, yeah, the maximum Robisco capacity, and S is the long-term CI over CA concentration. So you could set a finite limit, in fact, on the ability of the biosphere to uptake CO2, even in the limit of infinite CO2 concentrations. Okay, so these are just 2 points to point out. But now that we have the supply function dependent on the control variable stomatal conductance, we plug this back into the Hamiltonian. Now we have the carbon gain strictly dependent on the stomatal conductance, the water losses, yeah, based on Dalton's law, dependent on stomatal conductance and vapor pressure deficit. Now we have the Hamiltonian completely described by stomatal conductance. Now we can do some math on it, basically. And the math is pretty straightforward. All we need to do is just differentiate it with respect to stomatal conductance, set the outcome to 0, and solve for the stomatal conductance. That makes the Hamiltonian maximum. And if you do that, you find an explicit expression for the stomatal conductance that depends on the slope of the photosynthesis CI relation. And this is clearly now an outcome of the optimization theory. There is a -1 plus this quantity Ca over A lambda d. Ca is the atmospheric CO2 concentration, d is the vapor pressure deficit, and lambda is the Lagrange multiplier. I will show later that this -1 that arises from the optimality solution is entirely connected to the apparent feed-forward mechanism that Nadine touched upon yesterday. But because now we have an expression for stomatal conductance, we can predict what the long-term Ci over Ca is, and that itself varies with vapor pressure deficit to the 1/2, and we will explore a lot, actually, what that means. And also, we finally have an expression for photosynthesis as a function of Ca, the marginal water use efficiency, or the Lagrange multiplier lambda, the vapor pressure deficit, and atmospheric CO2. And that is basically the slope of the ACI curve that links photosynthesis to internal CO2 concentration. Now, it's quite clear to us that there is a clean relation also between photosynthesis and stomatal conductance. Notice the slope here and the slope here are the same. So if we take the slope here and set it equal to Fc divided by this quantity here, take this outcome and plug it back and do a little bit of algebra, lo and behold, you find that photosynthesis divided by Ca emerges on the right-hand side, stomatal conductance is on the left-hand side, and there is this quantity, square root of Ca over A lambda, that is now multiplying Fc over Ca, and there is an aridity index d to the -1/2 that pops up. This looks exactly like the equations of Ball and Berry and Liuning, except that now the linearity of Fc over Ca emerges or comes out of the optimization. It's not a priori assumed. The aridity index that we have been looking at, relative humidity or vapor pressure deficit, that was set in an ad hoc way by Ball, Berry, or Liuning, turns out to be d to the -1/2 from stomatal optimization theories. So these are all predictions that were made and can be compared, in fact, to these equations. Now, Belinda Medlin in 2011 had a variant on this derivation, slightly different result here, but by and large, the result is very similar. And she actually came up with this result assuming RUBP regeneration rather than a linear ACI curve. So her result is a little bit more general than this one. But it does suggest that no matter what the limitation is, whether a linear ACI curve or a nonlinear ACI curve, it seems that the tendency of stomatal conductance to scale linearly with Fc over Ca is as we say in mathematics, a strong result. Okay. Now, is there support for this? Sari Palmroth did a very nice experiment on Scott's spine. She actually did leaf gas exchange measurements across the climatic gradient going from Finland all the way down to Southern Europe, and she assembled a wealth of data sets on transpiration rates, vapor pressure deficit, and photosynthesis. And when she plotted transpiration rate on the y-axis against square root of vapor pressure deficit multiplied by 1.6 multiplied by this constant, lambda, and against photosynthesis, the data sets seems to have collapsed all on the same line, despite the fact that they have varied quite a bit in terms of climatic gradient. And that was somewhat an effective support for the fact that if stomatal conductance is multiplied by d, stomatal conductance varies as d to the -1/2 multiplied by d. So in fact, based on these optimality results, the transpiration rate should vary with the square root of vapor pressure deficit. Okay, so with this, we might ask, is this consistent with other results? Now, I will finish this and then we take a break. My colleague at Duke University, his office is next door to mine, thought that this problem was important. And so he, in 1999, had a paper that came up with an interesting result. So what Ram Oren noticed is that if he plotted stomatal conductance against some reference conductance, and he called this reference conductance as conductance derived at 1 kilopascal vapor pressure deficit, but well-watered conditions, high light, he found that, in fact, the vapor pressure deficit response is almost general for all species. He analyzed 30 or 40 of them for all species. It seems that GS over this reference conductance seemed to follow an expression of the form 1 minus m log d. And so he inferred m from 30 or 40 species, well, maybe 31 here, and found that m is between 0.5 and 0.6, highly constrained, okay? Highly constrained. But these were all well-watered conditions. Nadine actually showed the graph similar to this one in her talk yesterday. And so it suggests that irrespective of what the species is, it seems that for well-watered conditions, there may be at least one of the Jarvis functions may actually be more universal, okay? May actually be more universal than previously thought. Okay, so that's an important result to try to recover from stomatal optimization. I mean, if stomatal optimization cannot predict this summary of many species lumped together, then it's worthless, okay? Can we do that? Can we do that? So this is basically Ram's argument is that M is between 0.5 and 0.6, and when you plot stomatal conductance divided by this reference, this slope is very stable. So, okay, this is the solution that we have. So what's the connection between this and this? We can evaluate the stomatal conductance at 1 kilopascal and assume that the ACI slopes is still the same. So if you do that, you automatically notice that any Taylor series expansion of d to the minus 1/2 will have its first term to be 1 minus 1/2 log d plus a bunch of higher order corrections. And actually this series converges quite rapidly. In 3 terms, you are almost there. So if you take this linearization of d to the minus 1/2 and you do a little bit of algebra, you could show quickly that the d to the minus 1/2 result from stomatal optimization theory is exactly predicting a slope of 1/2 multiplied by this quantity. So, and this quantity is going to be slightly bigger than 1 because the numerator and the denominator are the same except that the denominator has a minus 1 in it. And what this quantity is, it turns out to be atmospheric CO2 divided by the marginal water use efficiency of the plants raised to the 1/2. And this number is way bigger than 1. So that's why the quantity here is going to be slightly bigger than 1, and that might explain why the result from Oren's work is between 0.5 and 0.6. So this is great. That doesn't prove that the stomatal optimization theory is correct, but at least it is getting the right vapor pressure deficit response. Now, typically, if you try to tease apart from data sets what happens, is there any check whether a log d or a d to the 1/2 is better description? Usually this is the sort of scatter that you will see in data sets, and from a fitting perspective, the data is not going to tell you which is better, but the two are very close. Okay, I mean usually for the range of vapor pressure deficits that we deal with, the two are pretty close. Okay, so I will take a break here and give you a few minutes to recoup, and then we continue on the apparent feed-forward mechanism, and then we finish the story on the leaves, and then we can continue with the discussion about what to do for the panel meetings. Yes. That's the next part, Harvey. That is the question that we're going to try to offer some ideas, not answers, just ideas. Yeah, Nadine. Yes. Yes. No, this was all assuming stomata. You could revise this, but then you would need to specify it. Of course, I totally agree. It's just that it is not controlled by stomates. That would be the. Of course. Sure. Sure. No. This is. I mean, also the nighttime transpiration is not considered. All of that. But what it's been done. Actually, it's been done. So you could add corticular conductance, and you could even add a mesophil conductance. But no, they don't. But from a stomatal optimization perspective, you could ask what happens if there is an extra water loss that is not controlled by the stomates. That can be done. but theoretically, you could rederive the same result by breaking actually the water flux into 2 compartments, stomatally controlled and non-stomatally controlled. As long as you can make the assumption that the corticular conductance does not depend on stomatal conductance, you could find analytic expressions that will embed the corticular conductance. But that is also an assumption that may be wrong, as you have shown yourself, because you have shown that if there is excessive drying, in fact, even the corticular conductance drops. So there may be some artificial correlation between stomatal conductance and corticular conductance. But if you are able to separate them and say that the rate of change of stomatal conductance to corticular conductance is 0, then you could rederive exactly the same arguments with the particular conductance embedded in it, but it has to be specified. Right. Right. So the separation, but in the end, it becomes almost uncontrolled by the plants, right? I mean, that the stomatal conductance almost becomes its own beast, and the plant does not give it orders anymore. It's leaking. Yeah, yeah, yeah. Oh, absolutely. But in fact, there is another way to do this, Nadine. Just not. Yeah, yeah. In fact, under those conditions, it will be interesting to see what happens to the Hamiltonian. The assumption here is that the Hamiltonian is positive. If the Hamiltonian drops to zero, you are dead. Okay, should we resettle again and continue? So we left this discussion about the vapor pressure deficit response of plants, and this by no means is a new topic. It's been almost en vogue every 20 years or so. Perhaps the idea of somehow plants anticipating atmospheric aridity has been around for a long time. It was perhaps articulated in a number of papers, including one by Detlef Schulze, where in 1972 he stated that stomatal responses to changes in humidity in plants growing in the desert somehow provide some sort of predictions. The plants, almost stomata, can predict that aridity in the atmosphere is going to continue and they are going to shut down before they desiccate. And the idea of the apparent feed-forward mechanism is pretty straightforward. If you plot transpiration on the y-axis against vapor pressure deficit on the x-axis, and what you find is that up to a certain point, the transpiration against vapor pressure deficit seems to be linear. As vapor pressure deficit increases and increases, it becomes more and more curvilinear. And so at some point, transpiration starts dropping with increasing vapor pressure deficit, despite the fact that the driving force for transpiration, which is vapor pressure deficit, continues to go down. So that would suggest that the stomatal conductance, as a function of vapor pressure deficit, is dropping faster than the driving force. And that generates this sort of curvature. And this sort of pattern has been observed before in many data sets. Again, these are some papers that are around that have reported those sorts of graphs, so you could see the exact source. And the question is, can stomatal optimization theories predict this sort of pattern? Or at least what do they give for this sort of pattern? Now, we have just established that if leaf conductance is proportional to some function of vapor pressure deficit, in this particular case, e to the minus 1/2, the driving force for leaf transpiration is proportional to vapor pressure deficit. These are all simplifications. Then the leaf transpiration, of course, has to be proportional to their product. So the apparent feed-forward mechanism has been viewed as a way that stomata is shutting down faster to prevent leaf dehydration. Now, some people have claimed that, hey, if this is truly an apparent feed-forward mechanism, it should also be reversible. In other words, if you reduce vapor pressure deficit, it should follow the same trajectory as increasing it. Okay, so this topic, as mentioned, started in the 70s, then in the mid-90s, so that's 20 years. This popped up again. Monteith came about to reinterpret the stomatal responses to humidity, and then a whole sequence of papers followed later by Mainzer and many others as to whether this apparent feed-forward mechanism exists and is real and can it be quantified, etc. Okay. So, from the stomatal optimization perspective, again, let's for mathematical brevity and compactness, let's just look at the result for the linear ACI curve where Rubisco limits photosynthesis. We have shown that the transpiration rate actually is written like this. This is basically taking the stomatal conductance result, multiplying it by vapor pressure deficit. And I've mentioned this -1 before, that this is primarily connected to the apparent feed-forward mechanism. Now I'm going to show you how. If you multiply the conductance by vapor pressure deficit, you get exactly the apparent feed-forward mechanism. You have a -d here, you have d to the 1/2 here, and this quantity here. So if you differentiate the transpiration rate with respect to vapor pressure deficit, set it to 0, you could basically solve where this maximum is. What would be the vapor pressure deficit where this maximum is? And it turns out that this maximum turns out to be at 1/4 the atmospheric CO2 normalized by the marginal water use efficiency. And so if the vapor pressure deficit exceeds this critical vapor pressure deficit, then we will see some apparent feed-forward mechanism. If the vapor pressure deficit is less than this D critical, your data set is not going to resolve it. And so the interesting thing is that whether you see apparent feed-forward mechanism or not has to be referenced to what you predict a priori the apparent feed-forward mechanism critical vapor pressure deficit is. Some data sets push the vapor pressure deficit quite a bit, and they don't see it, but they have never checked whether this condition is actually satisfied. And that's one case that popped up. For example, James Bunz in 1997 made the claim that the apparent feed-forward mechanism is all a load of crap, basically. But he had some good points. If you look at the data sets, yes, stomatal conductance does drop with vapor pressure deficit. However, if you look at the transpiration rate as a function of vapor pressure deficit, you don't see much apparent feed-forward mechanism. Now, if you use his data set to predict where this critical vapor pressure deficit is, it's hardly satisfied, in fact. So while he may be correct, it's difficult to judge from the data set alone whether the vapor pressure deficit was strong enough to see it or not. So this is just a cautionary point that sometimes you have to almost use models to plan experiments. I mean, if you are going to test a hypothesis, you better be able to make sure your experiment goes to the correct limits to be able to test it. Now, the more interesting one actually comes about from whether the apparent feed-forward mechanism is somehow connected to temperature responses. And this is basically work that Giulia Vico did in 2013, primarily to address whether the apparent feed-forward mechanism is consistent with the full optimality solution. And what she did is she plotted from the optimality solutions with no assumptions the transpiration rate as a function of vapor pressure deficit for Rubisco limitations, where she saw actually a little bit of an apparent feed-forward mechanism, and for RUBP regeneration, which she could show theoretically that the apparent feed-forward mechanism cannot exist. Remember that the linear ACI curve is associated with Rubisco limitations, not light limitations, because in fact, for light limitations, A becomes almost independent of CI. And in fact, she did something also quite clever. She changed the vapor pressure deficit in two ways. This is all model calculations. In one case, she actually held relative humidity constant and increased temperature. So she allowed all the photosynthetic parameters to adjust for these temperature changes. In another case, she actually held temperature constant and varied relative humidity. Now, if this result is general and only dependent on vapor pressure deficit, you should have seen the same apparent feed-forward mechanism curve. She does not. Okay, so that proves that a lot of the accentuation in the data sets of the apparent feed-forward mechanism may be temperature-driven, and that's why I'm saying that maybe James Bunz is correct, but not because of the experiment that he showed. However, even if you, and so this is actually the result here, so you could see that in the case of Rubisco limitations, you see a highly accentuated apparent feed-forward mechanism, but that is primarily due to temperature effects, on the photosynthetic parameters. However, even if you do the opposite, the Rubisco limitations will still exhibit apparent feed-forward mechanism, but you could prove mathematically that the light limitations or the RUBP regeneration mechanism will prevent it from happening. So this is an interesting result, strictly based on how you change vapor pressure deficit based on temperature or relative humidity. You could get an apparent feed-forward mechanism in your data or not. And that would suggest that if you take into account the temperature response of your photosynthetic parameters, you will blur basically the apparent feed-forward mechanism. Another thing that we have followed up on the stomatal optimization work was done by Valeria Volpi. She was visiting us at the time, and the Italians love their olive oil and spinach, and so there was some concern about what salinity might do to stomatal conductances. By no means this is a new topic, but attacking the effect of salinity using stomatal optimization is an interesting one. And salinity is quite different from droughts, okay, in the sense that salinity, in fact, changes so much the osmotic pressure that the mesophil system here, where photosynthesis happens, can contract or expand depending on the salt concentrations, and that is a structural change. So, in other words, you could material-wise, you could create an irreversible change in the mesophil structure. So, basically, expansion and contraction become irreversible. But the idea is as follows. Stomatal conductance, of course, is primarily driven by what is happening in the substomatal cavity and above it. However, photosynthesis actually does not happen in the substomatal cavity. It happens in the mesophil. And so you typically can add another conductance that goes from the substomatal cavity into the mesophil using the mesophil conductance. Now, the problem is that mathematically you are adding another resistance, but you're not adding new equations to close it. Yeah. So somehow, to close the problem mathematically, you need another expression for the mesophil conductance. But that doesn't mean that you cannot say what the mesophil conductance might be doing indirectly from stomatal optimization theory if you could predict a relation between the mesophil conductance and the other parameters. And that's exactly what Valeria started. She actually wrote the stomatal optimization theory as a combination of mesophil and stomatal, and made the assumption that the variations in stomatal conductance are not connected to the mesophil conductance. This is a very hard assumption, and I could easily punch holes in it by simply saying that if the leaf pressure is somehow connecting the mesophil and the stomatal, you are not going to satisfy this assumption. But that doesn't mean that we should not explore the consequence of this assumption on the relation between mesophil conductance and stomatal conductance, even though we know that this may be approximate and not entirely correct. So if you assume that the stomatal conductance does not vary with the mesophil conductance, they may be somewhat connected, but apparently Liang Honggu agreed that this may be a reasonable assumption, then you could solve for the stomatal conductance now as a function of the mesophil conductance. Okay, so you could find an expression between the two. And based on some measurements of cell CO2 concentrations that have their own problems, but still allow you to independently estimate the mesophil conductance, you could plot the mesophil conductance on one axis and the stomatal conductance on another axis, and actually see for the two species that Valeria has studied, olives and spinach, and those were selected for good reasons. One is salt tolerant, the spinach, and the olives are not very salt tolerant, okay? And so what you find is that in the case of olives being irrigated with fresh water, of course, stomatal conductance increases, and as mesophil conductance increases, so there is a little bit of connection between the two. These are all predictions, yeah? But for salt conditions, you could, the mesophil conductance can increase a lot, but primarily you are limited by stomatal conductance. In the case of, this is for olives, in the case of spinach, you find that almost the relation, the effect of salt is not as big as in the case of olives, but still the same patterns are correct, and the solid lines here, or the dashed lines, are model calculations. So you don't predict the mesophil conductance, but you could still predict the relation between stomatal conductance and mesophil conductance that seem to be reasonably followed by the data. And she also did quite a bit of calculation of how salt might impact the marginal water use efficiency, the Lagrange multiplier. And again, what she found is that for olives, there is a big separation. For spinach, there is not. Then this is basically the expression that she has. What she also found rather interesting is that if you plot now stomatal conductance as a function of photosynthesis, the linearity between stomatal conductance and Fc over Ca is not disturbed. In other words, the mesophil conductance is not altering that relation, even though it is finite and it could be somewhat affecting the outcome of the flux. Okay, so the interesting thing is that the stomatal conductance as a function of Fc over Ca seems to be robust, despite the fact that mesophil conductance still enters into the equations. Now, the problem with all of these optimality theories is that how do you go about specifying the marginal water use efficiency, or the Lagrange multiplier, lambda? That's a big issue. And what we're going to do now is suggest few lines of attack on this. And there are many others, including throwing away the maximization of carbon and simply assuming that plants operate to maximize transpiration, or plants maximize sugar transport, okay, rather than all these operations in the leaf. And of course, this is important. If you look at time series of volumetric soil moisture content, this is a graph taken from the Duke Forest over an 8-year period where soil moisture was measured on half-hourly time scale. And in this case, soil moisture is normalized by the porosity, so it goes from 0 to 1 in principle. You find that the resource availability, that we have bypassed by specifying the whole optimization, or anchored the whole optimization on transpiration, but we said it should be available water, fluctuates a lot, on many, many time scales. And so the question is, are these fluctuations so important that they would completely nullify the whole approach of Cowan and later revisions to it? And the answer is it depends. If you look at the spectra of soil moisture, which describe how much variability you have at different time scales, yeah, you find that the spectra of soil moisture content decay pretty rapidly at sub-daily timescales. And that would suggest that perhaps the variance there is not so crucial at very small timescale, but of course the variance is quite high at larger and larger timescales. Yeah? And that has been tested for many, many forests, and with Taro Nakai and others, there are now theoretical models that can predict the spectrum of soil moisture content from the spectrum of precipitation and some information about root zone soil moisture content, water uptake by plants and drainage. And those are all theoretical results, and primarily you could see that the spectrum of soil moisture content seemed to have an exponent that is a little bit steeper than -2. The -2 is the well-known reddening in soil moisture, and the excess that you see beyond -2 tends to come from precipitation spectra. The precipitation itself is autocorrelated, and that tends to actually steepen the spectrum of soil moisture. And that will be actually a subject for our review in soils in the lecture on soil moisture that we're going to present before Kari Jensen and Stefano come. So, yeah? No. Soil moisture does not have a very strong daily variations. Yeah, in all these conditions, it's not that strong. The transpiration rate has it, but not the soil moisture. Yeah, of course. Yeah, these are all, the root zone soil moisture. Yeah. Okay, so that might suggest that there is a timescale separation that would allow us to assume that perhaps lambda is constant on sub-daily timescale, but would vary on longer timescales. So with this, Stefano Manzoni decided to revisit the whole problem, but now looking at it from the available water itself rather than transpiration. So he wrote a hydrologic balance that said the rate of change of stored water in the rooting zone is rainfall minus transpiration minus other losses. And these other losses could be anything. Could be drainage, it could be competition with another rooting system, whatever you like. The objective function does not change. You are still interested in maximization of photosynthesis over a certain time period t, but now we have to specify a boundary condition on the objective function. So what do you do at the end of this time interval t? And that is often referred to as the terminal gain. And in fact, for our purposes, this terminal gain is basically telling us what is the value, yeah, of this water that you will leave in the rooting zone in carbon units, if you want an ecological interpretation. So if a plant is aggressively using water, it doesn't care about leaving any water in the rooting zone. But if a plant is adopting a very conservative strategy because of uncertainty in rainfall, you probably want to leave some water in the rooting zone. So in fact, this terminal gain, as we shall see in a minute, allows us to at least pit different strategies of plant water use in this optimality theory and link them to the operation of the stomates, the leaf. The Hamiltonian still follows the same thing, but now the marginal water use efficiency, or the Lagrange multiplier, has to vary on timescales. But again, these timescales are going to vary a little bit longer than the stomatal variations. And notice that this hydrologic balance actually is written on daily timescales and longer. Okay? And now you could derive an optimal stomatal conductance trajectory by differentiating this Hamiltonian with respect to the control variable stomatal conductance, with the condition that the time rate of change of the Lagrange multiplier is now dependent on the Hamiltonian with respect to the state variable, in this case, soil moisture. So this, under some conditions of losses, yeah, and some conditions of terminal gain, Stefano Manzoni is very good with this stuff. He was able to solve this problem for dry downs, single dry downs. And I will not show all the formulations, just to highlight again few features about this outcome. He actually showed that if you drop the terminal gain, so you don't care about what you leave as water in the rooting zone, and basically you assume that lambda is separated completely from the transpiration rate, the soil moisture content is roughly constant, you recover the classical, of course, Cowan-Farquhar approach. But if you allow soil moisture content to vary gradually, you discover that the marginal water use efficiency must go up in time. So the cost of water becomes more and more, or water becomes more and more valuable as the dry down progresses. That can be predicted. but the canonical features of the stomatal conductance vapor pressure deficit relation does not change. But in this case, if lambda is still a boundary condition on the optimization that needs to be specified, so you didn't gain yet much. However, what Stefano has shown is that you could still set different strategies, and they all for the terminal gain. So you could still specify different models that would vary with the state variable. So you could make g of t big or small as a function of soil moisture content that you leave at the end. And he showed that in all cases, you start with well-watered conditions for lambda, which is now a boundary condition, and that, of course, increases with time if leaf pressure becomes more and more negative, or stomatal conductance drops with time. And in fact, when you combine the two, you could show that the marginal water use efficiency, because time can be eliminated from both, now looks like it depends on the long-term pressure in the leaf. And so as time progresses, lambda, relative to its well-watered state value, becomes bigger and bigger and bigger, roughly at an exponential rate. These are all analytical results. And as usual with Stefano's work, he was able to compare these calculations with Avogadro's number of data points for herbaceous plants under arid and wet environments, deciduous broadleaf for arid and wet environments, as well as evergreen and conifers as well. So these are, a collage of probably 550 data points from different experiments normalized together. So now the problem is, how do we determine the marginal water use efficiency for well-watered condition? Well, Wilfred Conrad solved this problem for me, so we don't have to worry too much about it. Basically, you could derive it based on the geometry of the pores, okay? By equating the two formulations. One, how much you get in terms of maximum gas diffusion out, and you equate that to stomatal optimization theory, and so basically the two can be compared. And of course, this was the idea of Wilfred, but he used the solution of Jean-Yves Parlange and Paul Wagner, who first derived this result. Okay, we've talked a lot about the leaf. Now I would like to finish on a few points in the xylem and the phloem. Not as much as the leaf. Okay? We don't have enough time. Now the hydraulic transport system, the fact that there is some cavitation occurring, as Wilfred has mentioned and as Nadine has mentioned before, is not a new result. In fact, this is a quotation taken from Haberlantz's work in 1914. He actually stated that vessels and tracheids normally contain both air and water, the relative amounts of the two substances varying according to the season and the time of day. So the fact that cavitation existed in plants was known way before any new ideas about how to deal with it came about. So there was clear recognition that yes, plants operate in a normal way and they do cavitate. So this was basically coming from Haberland's work. So now we understand that cavitation and the formation of gas emboli are common occurrences in the xylem and many plant species. Okay, so now if we put the most detailed approach that we could put in terms of modeling water movement in the trees based on whatever we know about the cavitation curves or the vulnerability curves, put them all how they might vary with scale, put a realistic radiative forcing on the tree, have a fractal tree so there is some branching and so forth, and assume that the pressure in the roots are close to zero, and so therefore the pressure in the plant is going to drive everything. And these are simulations done by Gil Bohrer, and the model is published in Water Resources Research in 2005. Gil did this as part of his watershed hydrology project for my course. And basically the goal was to try to assess what would be the maximum hydraulic carrying capacity that can support photosynthesis under well-watered conditions. And so I will just run this movie. What you are going to see now are basically pressure distributions in the plants. And the red is something that crosses 1.5 megapascals negative pressure, and the blue is well-watered conditions. Also, I should also note that capacitance or storage of water is taken into account in these simulations. So now the day starts. Now we are close to noon, yeah, and then now we are going into the afternoon. Evening is the recharge. And so you could see that, let me play this again. You could see that basically the stresses in the plant are happening at the most distal part of the plants, and then later the refilling mechanism fixes everything, and then the plants actually was able to withdraw water from the storage and then resupplied from the soil. So this can be all modeled, but the point from these simulations is that can we at least simplify them and be able to interpret them in ways that would allow us to put many data sets together, and that is basically what we're going to now do. The premise here is that it seems that because the most distal parts of the plant have the most critical pressures, we're going to assume that the controlling pressure of water movement in the xylem is driven by the leaf pressure. And that's an assumption. So basically what we're going to do now is say, hey, let's look at this problem from a single resistor. We have pressure in the soil, we have pressure in the leaf, and we have the xylem hydraulic conductivity varying with the leaf pressure. Because primarily if the soil pressure is constant, you vary this one. That's the only thing that is going to change. So probably that's not a horrible assumption. Now, because the soil pressure is small relative to the leaf pressure under well-watered conditions, we're going to throw the soil pressure out. So the driving gradient to the whole problem is leaf pressure. And if we assume that the xylem hydraulic conductivity is primarily driven by this leaf pressure, this is not a new idea. This has been around for a while by Zimmerman. It was called the hydraulic segmentation hypothesis, in that cavitation occurs first in the most distal parts of the plants, and the simulation by Gill do provide evidence for that. And if we assume that we're not dealing with trees that are 120 meters, as Nadine mentioned, but we're dealing with trees that are more like 20 meters maybe, we could drop the gravitational potential relative to the pressure potential. So under those conditions, we can say that the maximum transpiration rate, because the soil is wet, the maximum transpiration rate that can be supplied to the leaf is dictated by the vulnerability curve, GP, that varies with the leaf pressure, multiplied by the leaf pressure, because the driving force is now entirely leaf pressure. Great. So now we have simplified the math a lot. Now we can do a lot with this simplified model. If you haven't figured out the theme of this lecture, it's all about simplification to the max. Yeah. Now, the vulnerability curve often is expressed as such. The vulnerability curve normalized by some maximum value drops as a function of leaf pressure, meaning you lose hydraulic conductivity. And there are many, many forms. Now I have a student working on theoretical models to predict the forms of these vulnerability curves from some basic thermodynamics and basic hydraulics. But basically a good fit to these models are power laws or Weibull functions or logistic curves. And basically they all say the same thing, that if you normalize the leaf pressure with respect to psi 50, which is the point at which hydraulic conductivity is impaired to 50% of its value, this is exactly the same shapes that Nadine has presented yesterday. They are whole plant vulnerability curve. So they're not incorporating one bubble in one element like Wilfried has mentioned, but they are a collage of many, many elements. The parameter A that you see here basically dictates how sharp the drop in conductivity is as a function of pressure. So if you want a very sharp drop, so you are either conductive or not conductive, then A is big. If A is small, you have a more gradual transition. So this is a very flexible function to play with. And if you do that, you find that the vulnerability curve requires three parameters: this curvature A, psi 50, and the maximum conductivity that you could allow. So if we put this formulation for a vulnerability curve here and try to ask what would be the maximum possible transpiration rate that you could supply to the leaf. As you increase the leaf pressure, of course, transpiration rate goes up, but the xylem hydraulic conductivity drops. So again, we have almost this interplay between increasing driving force and reduced conductivity, very much like the vapor pressure deficit problem. So you could actually proceed and find the maximum by differentiating E with respect to psi L, set it to 0, solve for the leaf pressure at maximum. That turns out to be dependent on psi 50 and the curvature parameter. And what would be the maximum E associated with this leaf pressure now can be computed. And you could also calculate GP at this pressure. And it turns out to be basically given by GP max and this curvature parameter. And so the percent loss of conductivity is 1 over A. So now we have three parameters that would allow us to diagnose how maximum transpiration rate occurs in plants. And that is giving us at least an anchor on how much water can be delivered to the leaves by the xylem system. So the solution is E max is GP max times psi 50 times A minus 1 to the 1 minus A over A based on this model. Now, if you do a sensitivity analysis, and Stefano has done this, so you take all the vulnerability curves that have been published in the literature, and you look at the value of A, it turns out to vary from 2 to 10, which is a lot. But this F of A that I show here varies from 0.5 to 0.7. So in the business of plants, between friends, we're not going to worry about this variation. So we're going to treat it roughly as a constant. If you do that, the concept between safety and efficiency immediately emerges, okay? Immediately emerges. It's actually the product of, so the maximum transpiration rate is actually the product of safety by efficiency. Efficiency is encoded in the maximum conductance. Safety is encoded in psi 50. And it is their product, ironically, that dictates the maximum transpiration rate, as simple as this, okay? GP max, basically, if you build an efficient if you build an efficient xylem system, you will have to have big vessels. Your psi 50 is going to be probably lower. So we don't have yet a super plant where we can increase psi 50 and GP max. Okay, we have not yet designed it, but basically it does suggest that for a maximum transpiration rate, there are a whole slew of strategies that you could achieve this maximum. You could be safe, so you have a high psi 50, but then you are not very efficient. Or you could be extremely efficient, but you are going to pay the price if there is uncertainty in pressures. So how well does this model compare to data sets? So again, Stefano is able to mine the literature big time, and he was able to derive something like 550 vulnerability curves. And then he went and assessed for different, he lumped these vulnerability curves for the different species in climatic zones: boreal, temperate, Mediterranean, tropical, and tropical moist and tropical dry. And then what he did is he basically found what would be the maximum transpiration rates for those species. Okay, so this was completely independent measures. They're not even the same experiments, not even the same location. Okay, and he plotted the modeled Emax from this equation against the measured Emax, yeah, where GP max and psi 50 were inferred from cavitation curves for species collected in those zones. And this is the comparison. So here Emax is plotted in cubic meters per day. So I told Stefano, this is nonsense. Sorry to tell you, man. Nice work, but this just tells me that big trees transpire more than small trees. So he came back to me and said, no, I actually looked at maximum transpiration rate, also normalized by sapwood area, and the agreement seems to be still okay. So that does suggest that at least GP max and psi 50 may reflect this trade-off between safety and efficiency, but you have to condition it on maximum transpiration. Okay, so alone, on their own, they don't say much. Yeah? But for a given maximum transpiration rate, you could compare now safety versus efficiency based on what GP max is and psi 50. And these are, by the way, measured from vulnerability curves. So we have a lot of that information. Okay, now I would like to touch a little bit on the phloem transport problem. This, again, was tackled in a very similar way by Jensen, so that's why I thought it would be nice to show it here. What Jensen did is he says, hey, look, if the sugar mass flux out of the loading phloem is given by the water flow rate multiplied by the density of water that may vary with sugar concentration multiplied by sugar concentration, so that's the water flux down through the phloem to the roots. It's an advective flux. The water flow rate is Q. And of course, the density still varies a little bit with the sugar concentration, but the driving force for that is the sugar concentration itself. Now, at low Reynolds number, which is the case for flow in the phloem, the flow rate is dependent on the pressure difference divided by the water viscosity. This is basically the Hagen-Poiseuille equation with just the geometric factors absorbed in one multiplier. Now, the water viscosity varies a lot with sugar concentration. Yeah? Think of maple syrup. Very sugary, but very viscous, yeah? So, and the pressure difference could have a hydrostatic component, but an osmotic component. And if we assume a linear osmotic pressure, which is what Jensen did, using the Van Hoff equation, then it is basically driven by the density multiplied by the concentration itself. So you take this pressure difference, you plug it here, you take this flow rate, you plug it here, now you have the flux strictly as a function of concentration of sugars. And you ask the question, what would be the sugar concentration in the phloem that would maximize this flux? Again, there is a trade-off, yeah? Because you increase sugar concentration, you increase the flux, but you decrease the viscosity in a very nonlinear way. This is very nonlinear. So I did this calculation again, and what you find is that if you plot the sugar concentration on the x-axis, the flux normalized by its maximum value, so we're not worried about units, on the y-axis, and you look at different approximations for the pressure drop, only hydrostatic, only osmotic, or their combination, you find that, yes, sure enough, there is a local maximum, and then, of course, if the sugar concentration drops, the ability to actually transport sugars in the phloem drops very rapidly. So this is a very touchy balance. And the optimum sugar concentration that you have is somewhere around here based on these model calculations. Very trivial, yeah? Very trivial calculations. In fact, if you look at the data set that have come about in terms of what the sugar concentrations are for many, many species, they're here broken up into averages for passive loaders and active loaders. You find that this is the range that they exist. This is the maximum that we are predicting. The two are pretty close. Okay, so this perhaps suggests that yes, plants have optimized their ability to transport sugar as well. Okay, but the approach is very similar to what we have just done for the water, and it is very similar to what we have done for the leaf. Putting it all together, Shang Wei, my former student who's now postdocing at University of New Mexico, did this, and he was able to show that if you combine water movement in the xylem, the leaf optimization, and transport in the phloem, and you maximize, in fact, the sugar transporting system alone, yeah, so you let everything be slave to it, because he found that the sugar concentrations is the most restricted, yeah, this is the most touchy. You could actually rederive the marginal water use efficiency of the Cow and Farquhar equation as a function of all the loading phloem properties and the maximum hydraulic conductivity in the xylem. So this is actually strictly based on a water balance, based on demand, supply, and transport. So I'm not going to go through this whole derivation, but basically now you could show that you could link the two. And other things pop up is that this marginal water use efficiency might actually scale with the square of the optimum sugar concentration, and you could predict analytically that the marginal water use efficiency has to drop with the conductance that varies with leaf pressure. So, and both of those, there is some support in the literature for them. Okay, so now I will conclude. We have shown that the stomatal control of transpiration allows maximum fluxes in well-watered conditions despite moderate cavitation. So this is basically suggestive that there is some coordination between the liquid and vapor conductances. We have also shown that optimal stomatal behavior is still possible despite downregulation of transpiration during droughts. And that is coming at the cost, at the expense of a marginal water use efficiency increase. So the price of water becomes higher, but it doesn't affect the general solution of the optimality arguments. Now, I should also comment on a recent paper that was published by Gleason in 2015, where they had a huge data set where they tried to find whether GP max and Psi50 are somehow correlated, and they found nothing. They conditioned the data on everything: temperature, soil, biome, species, you name it. None of these correlations popped up. They just did not do one thing. They did not condition their data on maximum transpiration. That was the only thing they did not do. Okay. Whereas our suggestions would be that if you are able to rank these data sets with maximum transpiration rate, for a given transpiration rate, you could see some relation between GP max and Psi50. So that would be an interesting inquiry to look into, but I did not do it yet. And then the last point is this connection between the end-member correction in the stomatal optimization theories and how leaves might operate. As I mentioned before, the objective function now has a terminal gain, basically, and one could simply link this terminal gain to the soil moisture state at the end of the integration period. And one could argue that if you want to assign a conservative water use strategy, you make this gain big, and if you want an aggressive water use efficiency, you could set this gain to 0. And then you could ask, what would be the optimal path that the stomata has to take for conservative water use strategies and aggressive water use strategies? Are they very different or not? What would be the impact on concentrations in the phloem? More important, what is their impact on this, so to speak, spectrum of isohydric to anisohydric behavior in terms of looking at relations between leaf pressure and stomatal conductance? So now analytically, or well, semi-analytically, one can explore these questions by looking at how to connect water use strategy, with the operation of stomates. And with this, I will stop. Thank you.